Hi everyone, welcome to this week's seminar. So today we will hear from Gabriel Pacheco Ribeiro from Universidade Federal de Pará. And so Gabriel is visiting us for a few months. And today the topic of the talk is about spectral signatures of gravitational decoupling hairy black holes. As usual, feel free to ask questions during the talk. There will also be time at the end. And Gabriel, thanks for giving the talk, and the floor is yours.
Okay, thank you. Good morning, everyone. So today I'm going to talk about some hairy black hole solutions that are generated by the gravitational decoupling framework. And initially, I'll talk a little bit about what are hairy black holes, what is the fundamental, or usually the most well-known results, and what is gravitational decoupling. So our story of black hole physics, or at least modern black hole physics, starts with the Schwarzschild solution, which is a spherical, symmetric, and static solution of Einstein's field equation, vacuum Einstein's field equation, which provides a geometry that has a structure called the David Weisman. And this structure really defines the divising of spacetimes in the sense that whichever object that comes in can never go out, classically. The story went on, and in 1915, the Schwarzschild solution was provided, but shortly after, Heisenberg and also provided the solution of the Einstein-Maxwell equation, which is the theory in which you couple gravity to electromagnetism. And then in 1963, there was a solution found by Roy Kerr of an axisymmetric black hole spacetime, which is a vacuum solution. So with this picture, we have a class of solutions there of black holes that are defined by three parameters: mass, charge, and angular momentum. Later on, John Wheeler conjectured that black holes have no hair. And this is a result that really states about the nature of black holes that are generated by a dynamical gravitational collapse process. So it is thought that whichever fields support the black hole, whichever fields compose the astrophysical object, astrophysical environment of a black hole solution, of a gravitational system, when under gravitational collapse, those complexities radiate away, and the black hole forms with only three parameters. So, in this sense, black holes are not complex systems; they are not hairy. In this sense, and so other parameters other than mass, charge, and angular momentum would be the black hole's hairs. So there is some important results that pointed this way. The first one is, one of the first one was Israel's theory, which states that if you consider an isolated system in a static space-time, then you find that the Schwarzschild metric is unique asymptotically flat from the static. Yeah, the static, yes, exactly. So the Schwarzschild metric is the unique asymptotically flat vacuum solution with a regular horizon. Well, there is a generalization of this outside spherical symmetry. So if you consider axisymmetric solutions, then you have the Gotham-Rawson theorem, which is basically uniqueness result theorem for the hair solution. So every one of those, it's the same thing as here, but now for axisymmetric spacetimes. And also you have some other results, such as the Bekenstein-low scalar theorem, which states that given some assumptions on the scalar field theory, you can show that a scalar field does not support a black hole in the sense that you find a contradiction within the proof. You find that if you assume there is a black hole solution with a regular event horizon, then the scalar field must be trivial. But you can evade some of those assumptions and find some hairy solutions. In a theoretical viewpoint, you could do, in principle, you could do so, which does not mean that those solutions are the final result of gravitational collapse. It just means that they are a solution of Einstein's field equation or any other gravitational theory. So, but to do so, we had to deal with the problem that Einstein's field equations are usually highly non-trivial to solve because they are a system of coupled nonlinear differential equations. So one might employ some techniques to solve those equations, and one of those techniques is known as the minimal geometric deformation. So this framework was originally developed in the brain world context, but it was soon found that this framework can also be used to generate solutions to Einstein's field equation. In general, you start from an isotropic seed solution, and then you can, via this method, generate an anisotropic solution. So basically, you consider Einstein's field equation, and you consider the stress energy tensor that is a composition of two other tensors, in which this alpha parameter is called the deformation parameter. So when alpha is equal to 0, you assume that the metric that solves the field equations, that is the matrix that solves this with just mu nu, is this, which is the seed metric, and it is a known metric in principle. Then when you turn on alpha, when alpha is not equal to 0, you have another solution, right? And the main idea about MGD is really that the addition of theta mu leads to deformation on the seed metric. And this deformation occurs only on the radial metric components.
Is there a symmetry which corresponds to the deformation, some group of symmetry?
What?
Is there a symmetry, group symmetry, which corresponds to the deformation?
I actually don't know the answer to this. If there is a group symmetry responsible,
like dilatations, conformal symmetry, and things like that.
Right, I would say that conformal symmetry would not be possible. In principle, because for conformal symmetry, you have to change also yes. So, but maybe there is some because this problem can actually be reversed. You can start it. I'll show later that it can actually be reversed. So maybe there is
some sort of one parametric family of solutions which are related to some one single parameter.
Yeah.
Thank you.
So
alpha is a small parameter.
yeah, alpha can be a big parameter, but it's usually it's free. So it's really the strength of the deformation. It gauges the strength of the deformation. So in the minimal geometric deformation, you assume that only the radial components of the metric is deformed. So indeed, the deformation is in this form. So why is this important? Why is this ansatz important? Because when we use these ansatz, we find that the Einstein's field equation actually leads to two different sets of field equations. The first one is Einstein's equation itself. The second one is a quasi-Einstein field equation. So the first set is solved by the seed metric, and the second set you have to solve. You have to make an educated guess and find the solutions. So the framework, the schema of the framework is basically this. Under the MGD decoupling, you start with a decoupler matter content, which is theta mu nu. You start with the isotropic generator, which is the seed metric, and it generally generates anisotropic solutions. So it generates an anisotropy. It was shown that the inverse problem can always be solved. So you can start with any anisotropic solution, and you can find the decoupler matter content and the isotropic generator. So you can always integrate back this problem to find this decoupling. So in some sense, you can always perceive one anisotropic solution as generated by a decoupler and an isotropic generator. Right, so now we'll talk about the extension of this method. So, which I'll call for short the gravitational decoupling. So the idea is basically the same. You have this composition of theta of the stress energy tensor as this. And once again, you have that when gravity is coupled onto this, you have a seed metric. And when alpha is turned on, you have this other metric. But now, the addition of theta mu deforms both the temporal and the radial components of the metric. So with this, you can assume you can right, with this assumption, you have the same problem. So you decouple the Einstein field equation to two sets. The first one is the Einstein field equation for for T mu nu, and the second one is a set of quasi-Einstein field equation. The difference here now is that we have one additional variable. So in comparison to NGD. So now we need to impose this in the second set some conditions, and well, it's preferable to impose physical conditions, and these physical conditions are energy conditions. So we can impose the weak energy condition, which states that energy densities must be non-negative. We can impose the strong energy condition, which with Einstein's equation, the Heisenberg equation, states that gravity is attractive via the frequency theorem. And you can impose the dominant energy condition, which is both the statement that energy is not that energy density is not negative and the matter flows in causal paths. So by imposing the stronger, the dominant energy conditions, in this paper they found two solutions. And while imposing the weak energy condition, it was found some other solution. Those solutions are basically, well, you do the whole gravitational decoupling, and then you impose the energy conditions, and you further impose that those solutions match the seed metric behavior far away from the horizon. So the metrics all take this form, and the weak energy condition is given by this, the strong is by this, and the dominant is by this. So in this kind of ad hoc imposures are made clear because, well, the weak energy condition, as one can see, is not okay.
The weak energy is from here is a function. It is a function. So how do you relate that? It's not obvious to me. You say the weak energy condition is given by the first expression.
No. The solution that you find, that one finds by imposing the weak energy condition in the gravitational decoupling method. You find some differential equations. You find the differential inequality actually, and then you must impose. Yes, and then yes, no, it's not an equation, and then you must give a guess and then do some fine tunings to find a solution.
Another question here.
So
what model do you solve? What you get a fluid or what you
this is basically an anisotropic fluid, but this is a sort of reverse engineering. So by imposing this, by guessing those solutions which satisfies all of those conditions, then you can do some reverse engineering and find what is the effective anisotropic fluid. So the main point here is that those solutions might or might not be able to enable us to test some other results in a conjecture on GR. Right. So first off, we start by
It's a little bit naive, but if you impose different energy conditions and you get different functions, does that mean that they're incompatible between each other?
Yes. This is a problem. This can be thought of as a problem because, well, those energy conditions, like the weak energy conditions, it's a part of the dominant energy condition. So one might assume that this should be a special case of this one. But since this comes from an inequality, that really we lose this type of behavior because we have to impose some general conditions on the inequality. So those functions, like the log function and the exponential function, they come from the constraint that they must match partial solution far away from. So one can guess other functions and find other constraints. But those additional functions are in some sense just guessing work.
Well, perhaps it would be clearer if you would say that these are compatible with the energy conditions.
Right.
Rather than determine the energy
Exactly.
conditions.
Yes.
right?
Yes. So we proceed by analyzing how light behaves around those black holes, and if they can provide some different phenomenology. So, for instance, by analyzing light, we are interested in no geodesics around these spacetimes. And while by considering spherical symmetry, static and spherical symmetric spacetimes, then one is led to some conserved quantities, and this equation for radio geodesics can be written, where this is the effective potential, which determines the behavior of the geodesics. So what do we know about the usual picture of light behavior around black holes and other objects? Well, for asymptotically flat black hole spacetimes, you have the function at the horizon is 0, and at infinity goes to 1. So this means that if the effective potential is proportional to this, that the effective potential is 0 at the horizon and 0 at infinity. But the effective potential is positive everywhere else because F is positive, then the effective potential must have a maximum. So the usual picture of the effective potential is a single barrier potential. And well, this is actually proved to be a very general result by Pedro. Yes. And in general, the stationary axisymmetric and asymptotically flat black hole with a topological spherical horizon admits at least one light ring. For ultra-compact objects, the picture changes. And now, ultra-compact objects, to be clear, means that you have a horizonless object compact enough to possess a light ring. So now the metric function is finite everywhere. And we assume also that it's asymptotically flat. So this means that not only the effective potential is positive everywhere, but at the origin it goes up, while at the asymptotic limit it goes to 0. So if it was so the effective potential is positive everywhere and finite. If we assume that there is an unstable light ring, since the effective potential, which means that there is a maximum on the effective potential, since the effective potential comes from plus infinity at the origin, then it must have a stable light ring before. So the usual picture is like this. So it goes to 0 at infinity. We assume that there is an unstable light ring. So since it comes from infinity, you must possess a stable light ring before. So this was also proved to be general. So light rings come in pairs, and this was true for axisymmetric spacetimes of ultra-compact objects. And then another nice idea was proposed in this paper. So it was conjectured that the existence of stable light rings outside the event horizon of a spherical symmetric spacetime occurs only if the stronger dominant energy condition is violated. So the functions that were obtained via the gravitational decoupling method can serve as a test ground for this conjecture. That's what we did. So for the analyzed spacetimes, in this you can see how fine-tuned those spacetimes must be. The strong energy condition, the dominant energy condition imposed on those metric functions establishes that those energy conditions are satisfied whenever R is bigger or equal to 2m. And for the weak energy, for the function associated with the weak energy condition, this energy condition is always satisfied when R is bigger or equal to this value. So we call this position REC for short. And the picture is this: you have a black hole with an event horizon, and then you have the event horizon has a position, and whenever this event horizon position is below this REC value, then you have a region. Necessarily, you have a region in which the energy condition is violated. So what happens is that this is important because those black hole spacetimes they possess configurations with multiple light rings. So you can find configurations of those spacetimes with multiple hyperlinks. So this is a plot of the parameter space, and this is the result of a scan on configurations of those spacetimes. So basically, you choose parameters of the spacetime, you find where the event horizon of the spacetime is, and then you find which configurations possess multiple icons. So for instance, all of those colored points are configurations in which you can find multiple icons. And the color corresponds to the position of the event horizon. So one can see that every configuration with multiple light rings violate the strong energy condition in some region of the spacetime. Because for all of those configurations, the event horizon radius is below 2m, basically. So every configuration of multiple light rings violates the strong energy condition. By doing the same analysis for the solution associated with the weak energy condition, one finds that there are some configurations with multiple light rings also. Remarkably, there are some solutions, there are some configurations with multiple light rings that satisfies the weak energy condition throughout spacetime in the outside region. So, for instance, one can investigate how geodesics propagate around those spacetimes. So, this is a plot that I made. Okay.
It's a question related to how you construct the solution, because I know that when you construct the solutions, you impose that a certain energy condition is satisfied everywhere, but now you're
this is the energy condition is a guiding principle, but you have to have, but other than the functional dependence, you have this constraint for the solutions to satisfy the energy conditions. So this can be a little confusing, but you impose some of the energy conditions on the functions, and you guess which function will satisfy the condition of matching the Schwarzschild solution in a far away limit, and then when you guess those functional dependence, when you impose that the energy conditions, you find that this is the constraint on those functions.
By matching the Schwarzschild that was in the far field, you mean one over R behavior?
Yes.
Extra steps.
Mm-hmm. So it's kind of a reversal. You have to guess because of the differential inequalities, and then you impose, and then you see when the guess, what is the real condition on the guesses.
You know, guess one over R squared as well, always. Yeah. So you took Schwarzschild, your guess functions is f. Yeah.
Mm-hmm.
You propose three functions f.
Yes.
Schwarzschild plus 1 over R squared. And then our terms are exponential or
logarithms. Yes.
And these are just guess. Yeah?
Yes. So okay. So when we analyze the first solution, we find that there is some configurations that you can find multiple light rings, and all those configurations violate the strong energy condition somewhere, which is not the case for the weak energy condition. So the weak energy condition is really not important in that it's not to be associated with the existence or not of multiple light rings. Because you can find configurations in which they possess multiple light rings while satisfying the weak energy condition everywhere. So this is a comparison of the behavior of scalar geodesics around two configurations, one with one light ring and other with multiple light rings. And well, to improve this analysis, we would like to understand the scattering of waves, like to improve the spectroscopy or spectroscopical knowledge of those solutions. So for doing so, we consider massless scalar waves, which are a simple case, which means that we have to solve the Klein-Walder equation in those backgrounds. And there is a separational variable, there is an answer that separates this differential equation into a Schrodinger-like radial equation, which is the regular equation, where this is the scattering potential. So this scattering potential possesses a nice property of for big L values, this coincides with the geodesic effective potential. So the picture here is basically that this contains all the information about the system geometry, and that the scattering analysis basically is the analysis of how an impinging wave is scattered transmitted by a potential barrier. So to solve this, we impose those boundary conditions, and we use the conservation of flux to really find a relation between the transmission coefficients and the reflection coefficient. And then we employ the partial waves method to find the total absorption cross-section as an infinite sum of the partial absorption cross-section, which is defined by the transmission coefficient. So we have some guiding principles to check our numerical analysis. For instance, in the low frequency regime, it established that the limit for omega going to 0 of the total absorption cross-section tends the surface area of the black hole vectorizing. While in the mid to high energy regime, we have that there is in general a universal oscillatory behavior of the total absorption cross-section, which is completely described by no geodesic observables, which is the Lyapunov exponent and the angular frequency. And of course, since the scattering potential and the geometric, the effective potential coincide in the high frequency regime, this tends to the geometric capture cross-section. So, right, and this can be shown. This equivalence can be shown by using the geometric optics ansatz, and one can show that the Klein-Gordon equation implies no propagation. So for configurations with one light ring, the basic picture is this: you have a single barrier structure of the potential, and well, when you can expect that if the potential barrier is higher, then the absorption will be lower, and if the potential is lower, the absorption will be higher. So this is the usual picture we get in black hole physics, spherically symmetric black hole. So the solid lines here is the numerical results, while the dashed lines are the simple approximation, and one can see that they coincide very nicely. But the existence of multiple light rings points to the emergence of trapec modes. And well, in the case of massless fields in spherical symmetry, those modes are commonly associated with the existence of multiple light rings, which is commonly associated with ultracompact objects. So, but now, in this case, the effective potential is more tractable than the scattering potential is more tractable than the effective potential, in the sense that for L equals 0, the scattering potential is given by this. So one can find that for a symptotically flat spacetime, a minimum always occurs if the metric function is not strictly increasing. And the metric function not being strictly increasing, actually to be precise, GTT being not monotonically increasing, implies in the violation of the energy condition. So there is some hint that there is a relation between the existence of this, although this is a sufficient condition, not a necessary condition. There is some hints that there is also relation between the existence of trapec modes in metrics of those in space-time described by metrics of these forms, and the violation of the strong energy condition. So we can do the same analysis now for the scattering potential, and we find regions in which there is potential well now. And well, what we find is that all of those configurations violate the strong energy condition somewhere in the outer region. But most importantly, what you see is that this region of configurations converge to the region of the existence of multiple light rings. So you could find configurations which possess a potential well and a scattering potential, and therefore might possess a trapped modes without the existence of multiple light rings. The same can be found for the weak energy condition, in which case the situation is the same. You have configurations that satisfy the weak energy condition everywhere outside the event horizon. So this is some examples. Those are some examples of scatter potentials which we analyzed. Those two are for the weak energy condition satisfying solution. This is for the would satisfied solution energy condition, because well, we know that if there is well on the potential, then it violates the energy condition somewhere in the outside the event horizon. So we focus on these two in these two spacetimes. Right. So the presence of the local minimum is associated with the trapped modes, whose frequencies can be calculated by matching solutions. So we consider quasi-normal mode boundary conditions, and then we solve them numerically the equation from the horizon to an intermediate region, and from this intermediate region to infinity, numerically. And then we match the solution in the intermediate region by making the solutions match smoothly. So those frequencies can also be related. It can be shown that they are also related to Bright-Wigner-like approximation. So in nuclear scattering, in nuclear physics, in resonance scattering, you have a Bright-Wigner approximation, and then it turns out that a structure resembling Bright-Wigner approximation for the scattering cross section can be found for black hole spacetimes. So this is valid just around this value. So one might see that around omega r, that is around when the frequency is the real value of those modes, there is a peak, a sharp peak. And well, by doing the matching of solutions, we find the modes, and indeed they are long-lived modes. And this is a picture of how would one use the Bright-Wigner-like approximation to extract those modes. So around these peaks of the transmission coefficient, you do a nonlinear fit with this model. And by knowing the real value of the trapped modes, you can extract the imaginary value. So, in conclusion, this is the total absorption cross section observed. So those sharp peaks are related to the real values of the frequencies of the trapped modes. And well, every vertical dashed line here is the position, is the value of real part of trapped modes calculated, numerically calculated, and one can see that they coincide. And I mean, it's worth stressing that those frequencies in this solid curve, they are calculated by imposing different boundary conditions. So there is a nice relation between them, although they are solutions of different boundary conditions. So this is the transmission coefficients, and it's in this that we can use the Bright-Wigner approximation to extract the modes. We just do linear and nonlinear fits around those sharp peaks. And well, this is another solution, and this in comparison is the Schwarzschild solution. So this, once again, you have sharp peaks, and this is, one can see that, well, the weight, the modes are not as effectively trapped as the previous configuration, but indeed you find vertical sharp peaks. And well, in conclusion, we see that the gravitational decoupling framework offers a robust platform for verifying the conjecture of Svetich and collaborators, which relates the existence of multiple light rings with violation of the strong energy condition or dominant energy condition. Our findings, numerical findings, support that the association between the existence of stable light rings and the violation of those energy conditions. Furthermore, we found that trapped modes might exist in configurations with a single light ring. So one might ask if the existence of trapped modes should also be associated with with violations of strong energy conditions, the stronger dominant energy condition, rather than the existence of multiple light rings, which is a possibility.
So the spherical token given states from the syncrotic flatness.
Sorry, flatness. Yes. So basically, if this is true, this might also be true, but there is no proof of this, and of course there is no proof of that. And this can be seen as a limiting case of that, although it's not clear that the regions, it is not clear that the regions that have the regions of permitted space that violate that have multiple light rings is completely on the domain of the regions that possess potential wellness scattering potential. So this is a nice way to test it, and it's a nice problem to try and solve. And well, with this, I conclude my presentation. So thank you very much.
Thanks, Gabriel. So we have time for more questions. Yes.
Coming back to this parameter alpha, so you include this parameter alpha, you assume that it can be big, and then you have a guess to find your new solution.
Yes.
But let's assume that this alpha is small, and consider it as a perturbation. Then, I guess, if you know your null order, this is what you call seed solution, I guess. Okay. If you know it analytically, then I guess, even in such a simple, such a complicated system of equation, you can write down your new solution analytically if alpha is small. I think it should be possible. And then you don't need to guess. You can just write it down straightforward.
Yes, it might be possible. I mean, well, we have to analyze the field equations, but
Maybe it's not good for your purposes to consider this parameter as a small perturbation, but what I try to say that if you consider it small, it's not necessary to guess.
yeah. Yes. But when you impose you would have still to impose the energy conditions, which would lead to differential inequalities. So I don't know.
You will not have a new problem in comparison with the problems you have now, yeah? It will simplify your life in any case. Even if you have some additional condition which you need to follow. Now you need to follow them, and if you consider this alpha is small, you will also need to follow them. So not additional problems, the same problem, but other things will be simpler.
Yeah, it's possible.
More questions? Are there any questions online?
I can ask the question.
Okay.
So are there any rotating solutions that have been found
Yes.
by these gravitational development?
Yes, there is. So some works about this. Actually, this is.
So there are deformations of curve, I guess. Is that it?
Yes, there is deformation curve. One of the things that I realized while doing this, I looked at the literature. There is such thing, but one thing that I found is that there was a lot of works that were investigating the quasi-normal modes of those solutions, and specifically one of them found that there is multiple light rings, so they were able to realize that the existence of multiple light rings. but the connection between this and the testing of the conjecture and the testing that if this solution satisfies the whole, the energy condition in the whole outer region was usually bypassed. It was kind of ignored, and I don't know how it is with solutions with angular momentum, but
But is the conjecture only for spherical spacetimes or?
only for spectrum, yes, only for spectrum.
We have to make a new conjecture
Yes.
for stationary systems.
Yeah, but it's only for static, yes. And well, there is a good point, because there is a paper in which the authors constructed a numerical solution, which apparently violates the conjecture. So, but the thing that they stress is that, well, it is a numerical solution. I could not be able to directly check, but what they stress in the paper is that you have to, well, you cannot have GTT times GRI equals -1. So for cases in which this is not satisfied, there is a case, they argue, that violates the conjecture. But they also argue that when GTT times GRI equals -1, the conjecture seems to be to hold still. So they checked a lot of configurations, a lot of solutions with multiple Lagranges, and they found that, well, this appears to be true, although one might further pose that GTT times GRI equals -1.
But just to clarify, the conjecture does not rely on that. It's more generally their paper.
It's more general.
For
yes.
any spherical,
For any spherical,
multi-Abelian
yes,
class
exactly.
spacetime.
Yeah, it's general.
Let me ask you a question, please. Back to the deformation of the metric. So I suppose all surveys will not be affected by this sort of information, like mass, Hitchman's curvature, everything remains the same, or it will be affected by it.
The asymptotic mass will not be affected.
Which is given by the asymptotic behavior of the vehicle.
Yes, actually, when you calculate the, for instance, go back. When you calculate the ADM mass for this spacetime, when you calculate the ADM mass for this spacetime, is just m.
So it's the same.
It's the same. But for those spacetimes, AM plus alpha L over 2.
Okay, what happens with Hitchman's curve?
What happens with?
Hitchman's curve.
The correction is given.
I did not investigate it.
Curvature.
Yes,
Curvature remains the same for all deformations you consider?
yeah, I don't know. I did not try to look into that. But well, there is
That's a
in this,
you know,
yeah, in this,
just taking something, you deform the symmetric by current,
right.
and then you deform the environments, which are no longer the same. So I work in a different space-time.
Okay.
It's different geometry. That's important.
Yeah, well,
But I still say we have seed, which is shorter.
uh-huh.
It's okay, but then you move to something different.
Right, yeah, the curvature will be, the scalar curvature will be different. The functional dependence on the parameters will be different, but the flow up at the origin will be
Right,
different.
and the deformation is not arbitrary, just what you wish.
Yes, in this sense.
I see.
I also have a question. I'm not sure I understood why this is called anisotropic, because it's spherical symmetry.
Right, yeah. So basically, the point is that the stress and the effective stress energy densities of an anisotropic fluid. So basically, it generates an anisotropy on space-time by doing so. So when you calculate the metric is not manifestly anisotropic, but the stress energy that generates it, the effective one, is anisotropic.
Radial and angular are different.
Yes.
Radial pressure and angular pressures are different, but it's
But
compatible
they
with
just,
spherical symmetry.
okay.
Yeah.
I see. Yes. More questions? Well, if not, Gabriel is still here for some time, so feel free to discuss with him later, and thank you again. That's it.